All right, it's 6 o'clock. Let us start. So first, I'll just introduce Andy first, and then I'll speak about the quiz for a couple of minutes, and then I'll ditch. So first of all, Andy Ferris. The people at home can also see you. The people at YouTube, nobody at home at the moment.
Hi, everyone.
I think arguably or unarguably one of the biggest Julia hackers of the Southern Hemisphere. That's a fair statement. So yeah, just so you know, I mean, stuff in Julia, like the static arrays package that everybody uses, including people where I work and many other places, created by Andy early on, and did a couple of postdocs and a lot of research in quantum physics after his PhD. Has been around the world. So really, yeah, pick on Andy for questions about the meaning of life.
I love questions.
Yes, so please do that. And thanks for those that have arrived. And if at home you cannot hear us, please say on the chat. Now, just a few things about the quiz. So, big homework, you've heard about that assignment, right? That's due this Friday. Last time to ask questions, tomorrow in person, tomorrow at 7:30 p.m. in the consultation hour with Paul Bellet and myself. So please don't ask the tutors questions about big homework tomorrow and onwards. Of course, if there's something administrative, we'll answer, and you can keep answering each other's questions in Ed up until the last minute. But just Wednesday night, we close incoming questions. We might finish answering them on Thursday morning in Ed, whatever there is. So good luck with that. Now, quiz, best prep for the quiz. First of all, big homework is great prep for the quiz. Oh, before I say prep for the quiz, how's the quiz done? So next Tuesday, this star, I guess that means we're at home. So each person is at home or in the library or in McDonald's or wherever you want to be, okay? You need to be at Zoom on start, but then you're not monitored on Zoom. We just trust you and you work independently. And you could use units 1, 2, and 3 of the course material online. So you could look at that stuff, but you can't get other help online. Okay. And in the end, like with big homework, you tell us your honesty statement, you record yourself, and we know the difference between a trembling voice and a kind of a true, honest voice. So this is my work. And, you know, that's so yeah, you just do the quiz. So it's all pen and paper. The quiz is, you can look at the quiz from 2021, from 2022, and the practice from 2021. So you've got 3 examples. The quiz this year would be of a similar nature. Okay, so some questions are quite straightforward and some stuff a bit more tricky, but yeah, you do need to get, I was just asked by Matt, you do need to get this expertise of kind of learning how to do things with pen and paper. So good prep for that, in addition to being in the tutorials this week for the quiz prep, good prep for that is to also just look at the lectures materials, unit 1, 2, and 3, and see that you can actually parse expressions and evaluate them in your head. Right? That's kind of, and you've built up that capability, I believe, already. Now, what Andy's going to start to do with you is unit 4. That is not quizable, but that knowledge will actually reinforce your quiz prep as well. So following the lectures, today's Andy's hour and Monday's 2 hours is actually also good quiz prep, although this material is not quizable. Yeah. Any questions? Okay, so there's a question in the chat.
Yeah.
Are we allowed to do the quiz on a tablet or iPad? Yes. So basically, you write on pen and paper or in a tablet and iPad. And 1 second, I'll get you in a sec. Right. So you write your answers, name on top, questions, etc. You get a bit of extra time. So allocate. Don't have a meeting at 7 p.m. next Tuesday. You get until 7:30 or something like that. We'll send the spec exactly. I forgot if 7:15 or 7:30 to take photos, upload it, and do that. So if you prefer on a tablet or iPad, go for it. Okay. Yeah, man. Sorry, I'm hearing.
Like, what's the time?
Oh, so the question was, what is the time allocated for reading? I'll be online for I forgot if the first 10 minutes or 7 minutes, it's written on there. And I'll answer questions online. So get the quiz, I'm online. You read the questions, read through it all, see that you can actually parse the quiz, understand it kind of, right? Everything. Ask questions about it, and then don't ask questions via chat, and I'll verbose everything to everyone. Okay. Others? All right, enjoy the core of Julia with Andy, and you'll see Andy again after, towards the end.
Yes. Oh, thank you very much, Yanni. I'll turn this one off.
There we go. Okay. Sweet. So my name is Andy Ferris, and I'm taking a few parts of this course. As you can kind of see from our list here, we're probably about a third the way through almost, getting towards a third anyway. So Paul Bullett's done a great job, I hope you feel, but I feel he's done a great job with the first few units, and we're going to cover some details about Julia. So you've seen a lot of Julia, but we're going to go in and I'm going to explain some of the rules of how it works so you can kind of have an understanding, clear up any confusion about some strange syntax you might have found, and you'll sort of have a much sort of deeper understanding. You'll be able to get in there at the end of this unit, you know, feel comfortable creating your own data types and creating functions that work on your data and things like that. So yeah. And then I'll go away for a little bit, and Paul Verbeek will come back and talk to you about our first project or the material that's related to the first project, which is computer algebra systems. So that this kind of flavor of like using computers to do mathematics, like we do mathematics with pen and paper. You know, we do integrals and things like that. And there's great software packages like Mathematica and Maple and so on that does that sort of stuff. And Paul has that background. Afterwards, I'm going to come back in units 6 and 7 and talk to you about data. And unit 8 might be machine learning, but it's that sort of thing, like manipulating data, tables of data, data frames, and also simulation. That's the other big part of that, simulation. Yeah. Okay, so that's it just for a little bit of sorry, getting my computers confused. Little bit of context of where we are in the unit in the course. But let's dig into unit 4. So I'm going to give you guys a little bit of a spiel. Okay, so I was here in the neighboring building, I believe, and when this course was still being designed by the University of Queensland. So this is the third year we've run this course, and Yoni's had this really great idea. I was really sold on this idea, that you guys can get some exposure to some different people doing mathematics on computers in the real world. Okay, so we do have some, like Paul Verbeek, academic here. So like, but the point is, once you do a maths degree or a related degree, you have a mathematical background, you're going to have a fraction of the cohort that's going to be very interested in academia, and you might do some pen and paper math. But the majority of the positions available, you know, in the world for mathematicians will be doing real world applications. And in the modern world, that's going to involve a lot of number crunching, a lot of computing. Okay, so I guess when I was sitting where you're sitting, well, as an undergraduate, I didn't get a lot of exposure to people outside the university. So it's been a real, I think, a good opportunity for me to come in here and have some fun with you guys. And I hope it's useful for you, along with the like perspective seminars. So why am I here? Why have we chosen Julia? Why? What am I trying to offer you in Unit 4? Okay. So my background, I did my PhD in the next building over here, the physics building. So with Matthew Davis, which some of you may know, and my sort of research in that was doing lots of simulations. So I would simulate boson-Sun condensates, and we would run them on a computer, and like you would end up with all sorts of interesting situations where you'd have very large simulations, for example, and you'd end up running them on a computer cluster, and you'd submit a job, and it would take, you know, a day to 2 weeks to kind of finish and come back and give you all the results from your simulation. That simulation might be something like solving partial differential equations or something like that. You saw with Paul, I believe, touched on solving a little bit of differential equations and taking little steps through time and stuff. So you can imagine doing that, but also you've got spatial dimensions, you know, this cloud of atoms moving around in 3 dimensions, doing very interesting things. So for that body of work, what we tended to use a couple of programming languages. Okay, so we used MATLAB and we used C. Okay, so C is a very low-level language. It's very close to the machine. So often we would do like prototyping work in MATLAB or entire simulations sometimes in MATLAB using this very high-level thing. So MATLAB was great. You could put in arrays of numbers and do number crunching at a very high level. The syntax and everything is written for mathematicians by mathematicians. Okay, and Julia actually takes 90% of its syntax from MATLAB. So that's sort of the history of that. But what would happen sometimes is your programs wouldn't run as fast in MATLAB. Okay, so the MATLAB compilers actually improved over the last 10, 15 years. But back then, if you're doing certain things, even an if statement might be 100 times slower than would be in C or something. So if you have a lot of branching logic and different things, it would actually be worthwhile as a researcher rewriting the code you've written in another programming language that was faster. And you see, today, there's a very similar story out there. You'll find people write a lot of research code in Python. And then there are bits that are slow, and they will wrap up those bits that are slow into C functions and call them from Python. Right, and that's how they make their Python code fast. So the context of how Julia became to exist was people doing this kind of work were a bit frustrated with the situation. They tried to create one language which at high level like Python and MATLAB, but was also very fast like C. Okay, so the reason why you need to care about speed is if you're doing mathematics and you're doing research, you're probably doing something which hasn't really been done before, right? You're sort of existing on the edge of what's possible. So if you're using a programming language that's 10 times or 100 times slower than your computer can be, you're probably asking, or you're probably only able to answer questions which people, like if you're doing research, for example, that people were able to answer by putting in more effort and writing their program in a lower level language a few years ago or 10 years ago. Okay, so if you're kind of out there at the extremes, you do have to care about performance, and you also have to care about how easy it is to do the thing you're doing, because it's probably pretty complicated and confusing. All right, and if you're doing a very large project, you have to be able to like involve multiple people in your code, and so there's lots of little things that you sort of have to worry about when you're doing this kind of mathematical work. After my PhD, I moved on to do some postdocs. I did a postdoc in Canada, I did a postdoc in Spain, again, studying physics, a lot of quantum information theory and simulations of quantum systems. You guys are in second year. If some of you have done quantum mechanics, you're probably familiar with entanglement, which is, a bit of a fuzzy concept, but what you end up having is if you have this massive explosion of state space where these different particles can be entangled with each other, and the system can be a superposition of many, many states. So if you have, say, qubits, which can be up or down, so that's 2 states per qubit, up or down. And if you had n qubits, the total state size of that system is 2 to the power of n. Okay, so that grows exponentially. If you had 10 qubits, that's 1,024 things. If you had 32 qubits, it's like 4 billion different states. If you have 64 qubits, we're starting to talk 10 to the 19 possible states already. And you don't have 10 to the 19 bytes of memory on your computer or on your hard drive or even in the cloud to kind of deal with that. So you have to, what my research was about was coming up with clever approximations to kind of like, algorithms and things that would let you handle these kinds of systems at scale, while still being somewhat accurate and fast enough to run on a modern computer. Okay. So again, that was a thing where we're doing these algorithm developments. We're trying to solve quantum problems that were hard to solve or hadn't been solved before. And you had to get the algorithm right, but you'd also have to have your code running fast to be competitive, or you would get nowhere. Well, after Spain, I came back to Brisbane and joined Fugro. If you all did, everyone come and see Dr. Megan Dawson? I think 2 weeks ago here. Megan, I think I thought it was a fabulous seminar. And I was working in very much exactly the same field. So just for some context, what we would do was fly airplanes and use LiDAR. So the LiDAR would shoot laser beams down to hit a point on the ground or a point in a tree and reflect back to the plane. Okay. And then from that, you could tell by the time that pulse took, however many nanoseconds, you divide that by the speed of light, so something like a measly 300,000 kilometers per second. And you'd figure out how many nanoseconds that was and how many, hundreds of meters away that was from the plane. When you do this, you don't just do one dot, right? You're doing millions and millions of dots, okay? So you'd fly a plane, you'd come back with a full hard drive. You'd be flying mini planes, you'd be trying to do something like cover some fraction of Queensland or something, and it was ridiculous amounts of data. Maybe petabytes, this kind of data. So that's like, does anyone know what a petabyte is? Can anyone tell me what a petabyte is? Yeah. Terabytes, yeah. So it's not the next order of magnitude, it's the next power or multiple of 1024. Right. So it's 1024 terabytes. So a terabyte is roughly what you'd come on a hard drive on a relatively powerful computer these days. Okay, so we're talking like 1,000 hard drives, right? And you might have to deal with that. Interesting things that came up, I thought at Fugro was even the physical aspect of moving that much data. Moving so many hard drives around the country would cost a significant amount of money, such that buying hard drives were a bit more expensive, but were lighter, would reduce your postage costs by, many thousands or tens of thousands of dollars per year. It was very, very interesting space that you have so much data, you kind of have to be very careful how you deal with it, how you transport it, how you store it, and we'd end up using, the cloud services, where you have services like S3 and you can put lots of files on S3, and you have computers that you can rent and do the processing of the data, okay? Now, when you have that much data, you also have to be careful about the processing time, the processing cost. So again, if you're doing something new industrially that hasn't been done before, it involves a lot of data, you're gonna have to crunch a lot of numbers, and you're gonna have to do that fast. So you're gonna have to apply interesting algorithms. So in that space, if you remember from Megan, they were like inferring where the power lines were and the ground was and the poles were and the trees were, and trying to figure out what might be going wrong. Like, is a fire going to start because the tree's touching the power line, or is the power line too low and a truck might run into it, and things like this. So you really have to have clever algorithms. So you have to bring your sort of maths brain to bear on the problem and solve this. But you also have to be a good programmer and make the computer crunch those numbers quickly. Because if a good fraction of your budget is the computer, and your computer program runs 10 times slower than it otherwise could, because it's not very efficient, say, you might go bankrupt. You might literally, it might take too long to process the data, or you might not be able to do things you could otherwise do. Another thing you can do, I came across problems in this space where if you took a problem and you redesigned the algorithm and rewrote it into a faster language, you might actually solve this problem 1,000 times faster. And so you get into a regime where you had problems which you'd normally do offline, like overnight or something, and suddenly you're doing it in real time with a human interacting with it and clicking it, and it's inferring things, and you can have this dynamic between the computer sort of AI system almost, inferring things for you, and you're checking them as you go, and it kind of like it's sort of symbiotic. After I was at Fugro for 4 years, overlapped with Megan a little bit. And after that, I moved on to a startup called Alara. And we're a Brisbane-based startup. We're pretty small. We do simulations of business systems and optimizing of businesses. As I alluded to a little bit earlier, Unit 6 or 7 is dealing with simulation. And I'll talk more about my background with simulating businesses there. That'll be much more relevant. Okay. Cool. so that was just a whole bunch of context, and I'm sorry for speaking about me so much, but I think it's a good opportunity that you guys get to meet and see different people throughout this course. So what we're going to talk about here is how we need a programming language which has these aims in mind. We want a programming language which has a quick execution speed, right? A programming language which is quick to code, like you can solve mathematical problems, you can bang them out. You don't need to suddenly think like a computer and deal with pointers and all sorts of memory allocations and things. Something where you can write the code, you can edit your code, and it doesn't just turn into a mess, a tar pit. So an interesting thing, which wasn't obvious maybe in the 60s or 50s when computer programming languages were first coming out, is that as you write larger and larger programs, some programming languages tend towards this problem that the code sort of becomes very hard to read, very hard to edit, and stuff. So programming language designers have to be very careful about creating a system that's easy for people to come in and add new features or whatever to an existing system without kind of making it more complex. Okay, so in units 1 and 2 and 3, you've sort of looked at the basics of Julia and computing, basic data structures, basic numerics and things. We're going to cycle back and talk about how Julia works, so that we're all on the same page. We're not going to look at a piece of syntax and get confused. We're not going to see, oh, why is it behave like this kind of thing. So it's sort of like we'll probably go through a few hours of lectures here, but you'll actually end up with a really comprehensive list of exactly how Julia works. So this is going to help you with your future projects where you're going to be writing the code, and you need to be comfortable creating a data type and comfortable creating functions of that data type to get your work done, your algorithms in and stuff. Okay. Yeah. So Julia is the language we're using for this course. Different programming languages just have different design goals. They're for different purposes. Some are designed to write web servers, but we're not here writing web servers. We're trying to solve complex mathematical problems. So Julia is I won't read out what's written here, but the goal here is to show the most important parts of Julia, and to sort of just show you how it achieves these 3 goals. It runs fast, it's easy to write, it's easy to scale. Okay. All right. So you don't have any questions before we dig right in? Cool. Okay, so one of the things we tend to do with maths is we write all these things on where's my pen? We tend to write equations down. We work a lot with a lot of mathematical objects, and we write a lot of things like an integral or something, whatever it is, and we have a lot of these objects in this thing, which are kind of like we write down in a way. Okay, so mathematics is often about having these various different objects here, how they relate to each other, how they transform under operations, how they behave, and that kind of thing. So Julia is very much related around values and objects. Okay, so as a programming language, some of the ways that this is done is one little fact is all Julia code that's valid is an expression. Okay, so everything that is a piece of Julia code returns a value. Okay, and I'll explain what that means in quite some detail in a minute. Okay, every value has a specific type. Okay, so if I look at an equation like this, we might know that x is a real number, for example, and Julia is the same. And functions themselves are also things we can represent and transform. We've got lots of higher order mathematics and category theory and all sorts of things you can do. if you want, and you can also kind of represent those kind of mathematics in Julia. And so that's a relatively common list of features there. A couple ones which are a bit less common, but are probably ones that types in Julia are also values. You can get a type, you can manipulate a type, you can pass the type to a function, which could return you another type. And Julia code itself is also a value that you can pass around and interact with. And so that lets you write macros and do all sorts of meta programming, and you can inspect at runtime all the generated code and things like that. Okay, so that's pretty powerful stuff. In fact, they let you write the Julia compiler in Julia, which is sort of how it works. But we're not really going to focus on those last two. But I'm going to go into some detail of what I mean by expressions and values and types and functions. Okay, so this isn't an accident. Like I said, this is really created this way to make it easy for mathematicians to write code, which is easy for the computer to run fast. Okay. So you know, as I mentioned, in maths, we're interested in objects and values. So types let us. So every value in Julia has a type. The fact that we have these types, what is a type? I'll talk about exactly what that is in a minute. But types let us specify the data that we have, or whatever it is, the object, the data that corresponds to an object. But it also lets us define the behavior of all the functions that interact with that type of object. Okay. We also types also help the computer. Okay, so types help the compiler know the exact representation of data. Okay, in memory, like how many bits is it? If I want to multiply it, what CPU operation does that correspond to, and things like that. Okay, and with this, it can sort of in advance compile some really nice fast code for you and run that, you know, maybe many times over in a loop or something. Okay, so the types in Julia, and we'll talk a lot about types to get through everything, multiple dispatch and everything, is for two purposes. It's for the humans and it's for the computer. Okay, and they really do serve these goals that I was talking about at the top. They make it run fast. They help you write things easily, and they also keep things separate in a nice way that makes your code not turn into spaghetti when you write more complex programs. So the first thing I mentioned is all valid codes and expressions. So what's an expression? So expression is just any bit of syntax or whatever in Julia that you can run. So here's some expressions like 1 + 1. I might just get this up. We can do some nice. Okay, that should be nice and big. So like that's an expression, right? So 1 is an expression with the number 1 in it. 1 + 1 is an expression, and it can evaluate to 2. You know, 1 + 1 + 2 is also an expression. So expressions can be arbitrarily big, but whenever you type anything in Julia that runs, it always returns a value. Okay, so some programming languages don't really have this property. They have statements. So in C, you might have statements. In Python, you might have statements. When everything is expression, it's very easy to like copy and paste code and put it somewhere else. But if you take something like Python, it becomes a bit annoying to kind of like take a big complex bit of code and put it in a lambda in Python, because Python lambda can only accept expressions and not statements, and it sort of gets all messy. Okay, and the reason why programming languages originally had statements is people thought of them as recipes for the computer to follow. So it's like computer do step 1, computer do step 2, computer do step 3. Whereas I think in mathematics, you're a little bit more freeform about letting the computer solve the best way to solve, the problem. It's still an imperative language, very algorithmic and imperative language, but it lets you kind of think of everything with a value. Everything is an object, everything has a value, and every object has a type. Okay. So, for example, for every expression, you always assign it to a variable, right? Even if it's something like print line. So print line is something which does something. It doesn't really normally return something, but it does have a value. Every value in Julia has a specific concrete type. So you know, if you evaluate an expression, you get something back. So if you do type of 1 + 1, that's the same as type of 2, and 2 is an integer. Specifically, it's a 64-bit signed integer. And that requires like 8 bytes of memory to store that. Okay. So when you have a number like this, the Julia compiler can sort of reserve the memory in advance. Say, oh, what we're going to have of this number, it's going to need somewhere to sit on the stack that's 8 bytes long, and we're going to put the number there. Okay. So the type of the second thing there is just oh, it didn't actually come up with that one. Why didn't it come up with that one? That's weird. But you know, the type of that is this vector string. Okay, so you would have come across arrays and vectors already quite a lot. But I'll talk more about what it's talking about with aliases and stuff in a minute. But this vector kind of knows that what's inside it are strings. Okay, it sort of has this sort of knowledge of what's inside of it, which again is something to help you and to help the computer. And then there's this weird one here. So print line puts things on the screen and puts a new line at the end. That's the ln part. And that's why we see this pi here. So it doesn't normally like return something specific, right? It doesn't. But what it does do is it returns this thing called nothing. Okay. So the type of whatever it returned was nothing. Okay. And nothing's nothing special in Julia. It's just like any other data type, and we'll talk more about that in a minute. Okay. But nothing is included in Julia just literally for this purpose, for being this placeholder where stuff doesn't really need to be anything in particular. But it means the language doesn't have to have weird statements and weird syntax. Okay, so every one of these values is what's called a concrete type. And we're going to talk a lot about concrete types, and then we're going to talk a lot about abstract types. All right. So concrete type is the type of an actual value, and a concrete type defines things like how's it laid out in RAM, you know, and what functions can you call with it and things like that. Okay, so there are only a very small number of possible concrete types in Julia, or types of kinds of concrete types. There's primitive types, there's structs and things which are like structs, arrays, and then strings are kind of special. Okay, but strings are there too. So that's not very many. So basically, if you know how to deal with these 4 things, you can create any possible piece of data in Julia that's possible to create in Julia. Okay, that's all there is. Everything's in here. Every function, every piece of code is going to be just one of these things, or some composition of these things. So primitive types are primitive. They don't really have any structure. They're just a number of bits. Okay, so like uint8, which is our byte type. We'll just you've probably interacted with a little bit, but uint8 is numbers like this in hexadecimal, and it's 8 bits long. It's 1 byte. It has values from 0 to 255. In hexadecimal, 255 is FF. So F is the largest hexadecimal digit. So that's the kind of range of them. And there's exactly 256 possible values which are uint8, which are distinct. Okay. So what you can think of as every type in Julia is like a set of values that are possible, if that makes sense. Okay. So uint8 has a set of 256 possible things. If I look at something like int64 and float64, they're literally defined in Julia like this, right? Like they're 100%, that's all they are. All right. You can define your own primitive types. It's not like has to be built into the compiler in a very special way or anything. So they are defined very similarly. They both have 64 bits, but they are different types. So each of those are sets that have about 2 to the 64 or about 10 to the 18 kind of 19, 18, something like that, possible values, right? But for each value in the program, Julia doesn't only know like those 64 bits, it also kind of knows either at runtime or at compile time what the type of that is, okay? So if you take, say, all the bits, all 64 bits are 0, right? And you convert that to a float 64, it's 0.0. It's sort of like you can take those bits and convert to another type using this reinterpret function, right? But they're different things. 0 and 0.0 are different objects in Julia. So if you want to think about it here, I just want to be able to see this camera here. How big is this whiteboard space? All right, cool. Yeah. So you can kind of think, you know, with U in A, you know, you might have this set of different 256 different things, right? And when I define int 64, I'm creating this other set with 2 to the 64 different things in it. And when I'm creating float 64, I'm actually expanding the universe. There's a distinct set of a new 2 to the 64 different values that are there. So every time you introduce a type, you're creating new possible values in the universe of possible values in Julia, okay? So Julia's, you know, in a sense, you can extend Julia to include more types, your own types that you're interested in, that helps you solve your problem. Okay, that might not just be adding floats and integers. Okay, so like I said, Julia will kind of know the type of things. If it can figure that out at compile time, it'll quote unquote erase the type. So at runtime, you don't need to keep any extra bits around tagging that this value is an int and that value is a float. It will know at compile time. It'll tell the CPU to load things in the right register and stuff for you. But if it can't do that for some reason, it can just like interpret your code. It will add a little tag to every value, like a pointer to a type, and it can dynamically figure out the type of that thing. All right. So a little note here is primitive types are immutable. You don't edit these bits. Like you don't edit the number 1 and turn it into the number 2, because that would turn all the number 1s in your computer into number 2s or something. That'd just be weird and mind-blowing. What you do is you create a new set of bits, and maybe you overwrite, maybe the CPU gets overwritten in the same register or something, but semantically, in terms of Julia, you're not editing these primitive types. Structs, I think, have you guys seen structs yet? Did that come up yet? Or are these new? A little, yeah. So structs are in almost every language has something like structs or records or dictionaries or something like that. So structs let you basically name different, put pieces of data together. So that the purpose of a struct is you're creating a data structure with multiple bits of data inside it. And for example, a complex number might consist of a real component and an imaginary component. And you can define a struct in this syntax in Julia. The double colons kind of indicates the type of something. You might see this when you define a function as well. We'll talk more about the double colon later. But this is how you define like a complex number, which consists of 2 float 64s. You know, you kind of can tell that this thing needs 128 bits of data to store because it has 2 64-bit things in it. And when you define this struct, once again, like here, you're creating a new set of possible values, which is distinct from, even if you create another struct with fields re and im, which are float 64s, it's a distinct new set of values, okay? It's new type, new set of values. When you define a struct, you kind of get this function on the type, which is interesting. So remember, types are objects. In Julia, you can assign functions to everything, and so it creates this constructor function, which lets you define the values of the fields and construct that struct. Okay. Once you have that value z, right? The size of z is 16 bytes, 128 bits, and you can get stuff out of the struct with the dot operator, .re, .im. Okay. So I think everyone would have seen this or kind of understand this, but it's just worth going through defining it. An interesting thing you can do is define a struct with no fields. So how many bytes will that need to represent something with no fields? 0 bytes. How many different distinct values are there in a struct with no fields? So if I have a uint 8, it has 8 bits, I can do 256 values. If I have a bool, right? If I have bool, there's only true and false for 1 bit. If there's 0 bits, how many possible distinct values are there? Or are any values possible at all? Is it not possible to construct? 1, okay? So here, if there's 8 bits, there's 2 to the 8 possible values. If there's 1 bit for Boolean, that's like 2 to the 1. And one of these things is 2 to the 0. So 2 to the power of 0 is 1. There's 1 possible value. In Julia, I mentioned this nothing before. There's this type nothing with a capital N. Types usually have capital letters. That's just a convention. It's not a rule. Called nothing, and it's literally defined this way again in the compiler. There's this type nothing, and there's this constant instance of nothing with the lowercase nothing. And this is what's returned by functions that sort of do something but don't really compute something and give it back to you. All right. It's also used in bits of syntax which you wouldn't expect to return a value. Okay. So interestingly here, now you have a one-to-one correspondence between the type and its singleton value. And these are called singleton types. Okay. Another thing to cover are mutable structs. So if you use this mutable keyword, so this is exactly like the one above there, except I've stuck mutable in front. This now means the values in that struct can be edited. So it's standard struct, but default you can't swap out those fields. They're stuck there. Okay. Now they might be arrays which can be mutated or something underneath, but at that layer of nesting, you can't swap out that value. It's stuck there forever. In a mutable struct, you can change things. So you can do like z.im equals 0. Previously, that would have thrown an error because z's immutable, and so you can't change it. Right. And again, for things like numbers, it doesn't make sense to mutate a number. You compute a new number from old numbers and operations and stuff. Right? Generic types. So this is probably where we're getting to things, syntax you would have seen. Maybe if you haven't used other programming languages, might be a little bit confusing. So in general, a complex number, we talk about it, it's a number with a real component and an imaginary component, right? But we could talk about complex real numbers. We could talk about complex integers in mathematics. So I'm just talking about pen and paper. We could talk about hyperreal numbers and making complex number out of hyperreals and things like this, okay? And it's the same in Julia. On a computer, you might be interested in using float 64 or float 32, which might be a bit faster and use less memory, or something like that, okay? So this little thing here, this curly braces indicate a generic type. So what this means is it makes a whole family of types. Given a T, you get a concrete struct, and you get to insert that T into the fields. Right. So in all the fields, you could write something different, and they could all be different. They may or may not use T, but generally, this is a generic type or an abstract type, and given the T, you get this concrete type of all these things. So with the complex numbers, you end up with a whole set of complex numbers for complex int64, and a whole set of different and distinct complex numbers for complex of float 64. And for float 32 and so on, okay? So it creates this entire family or set of sets of values, if you'd like to think of it that way. Yeah. So, and of course, this is useful because as someone, say, writing the Julia call library, base library, You can define complex numbers, and you know about how to take the conjugate of a complex number and how to multiply complex numbers. But you can't really anticipate all the kinds of numbers that your users might want to use. You know, you might include float 32 and float 64, but they might end up using, you know, a GPU, a graphics accelerator, with doing neural networks with some floating point representation you haven't even thought of. And it'd be kind of cool if they could still use your complex type, right? So this defines a whole family of types, you know, not even anticipating certain T's that might not even exist when you've written this, okay? So if I take something like abs2, which is the function which takes the square of the absolute value of a number or a complex number, you could define it like this, and that would work perfectly fine for any of those T's, for integers, for floats, or for whatever, for rationals, you know. Cool. Type aliases are very simple. You can just define something as being, you know, you can just sort of manipulate types and store types as variables, right? So here we're creating this. This is just a variable. It's also a variable that contains a type, but it's literally just a variable with a capital letter in front, right? And it's just equal to this type here. What we do is we stick a constant in front of it, and that just helps the compiler know that's not changing over time. It can do constant propagation with this. It can do type inference using that. Okay. So that's generic structs and type aliases. Tuples. Tuples are another type in Julia that you've probably come across. Maybe hiding a little bit, okay? So if you think of how you call a function in Julia, you know, you might, you know, you can go like, you know, sine of 2, or you can go plus of 1 and 3 or something. You can sort of see these brackets with commas and a list of things in them, but you don't need the function. You can talk about that set of parameters in the abstract sense, and that's a tuple, okay? It's a lot like a struct, right? So that this is my tuple, right? Or they could all be different types, you know, they could be something like that. And you can kind of start indexing it and getting different things out of it, right? And because it's a struct, the different fields or different, you know, places in there, they can be different types, and that's okay. Okay. But basically, it's like a struct. It's sort of anonymous. It doesn't really have a name. And it doesn't have field names either. Now, there's another thing called a name tuple, which doesn't have a name, but does have field names. Okay, and that looks a lot like the keyword arguments you see in functions. Arrays are the other kind of major thing in Julia. You would have already played with arrays. So this is not where with structs, you can combine like 2 things or 3 things. But if you have a dynamic number of things that depend on the data at runtime, this is where you start using arrays. You have some number of integers, or you have some number of floats, or you have some number of strings, and you want to put them in something. That's what an array is for, okay? So typically when you're just collecting stuff, you'd use a 1-dimensional array or a vector, okay? Vector is just like a type alias for an array which is 1-dimensional, where the n here is set to 1. Matrix is obviously, oh, by the way, those 2 are backwards. I should fix that. Yeah. And the other thing about arrays is arrays are always mutable. You can mutate them. You can edit them in place, okay? So you can construct array, and then you can append things to the end, and then you can edit the element in the middle and do all this stuff at runtime. And you know, all this talk about values and immutable and transformations and things is well and good, but at the end of the day, Julia is also very pragmatic and lets you write quite quick algorithms using, you know, all the power of your computer. So it's not like Haskell or something where it's very dogmatic about everything being immutable. Yeah. Strings in Julia are built in. They're a special type. They're a lot like an array of bytes or array of characters. The one difference really is that they're immutable. Okay, it doesn't really make sense. Like if you pass a string to a printing function and then the value of that string changes or something, it's very easy to get yourself confused with strings that are being edited in place as objects. in programming languages. And so many modern programming languages these days will have this pattern that the strings can't be edited in place. You can concatenate them together and do different operations when you want to create new strings. And that's it. So everything in Julia, even types, even functions, modules, all these things, they're literally just these things. Okay. And you can build them all, right? You've seen the syntax. You can just go struct, name, fields, hint, right? So that's it. So I just didn't want things to be mysterious, right? That's what we got to do. It is 6:50. It's a 50-minute lecture, I believe. So what we'll do is we'll call it and we'll come back and talk about how to, we expressed every possible way to get a piece of data into Julia, right? From here on, we're going to talk about logic, right? How do we manipulate that data? How do we define functions on that data? And so we're going to start with the syntax of like expressions and things, and then like you can put all those expressions inside functions. And then we'll talk about generic, like how you can use multiple dispatch and create interesting functions that can take different types. Then we'll talk about abstract types. I did mention what concrete and abstract types were. All an abstract type is like, it's still got to do with, types are still sets of values, but you can take maybe say 2 of these kind of sets and put them together, and that's like an abstract type. Okay. And so sometimes you might be interested in functions that are defined for all numbers. For example, you don't care whether it's that number or that type or float 32 or whatever. And this is where you use abstract types in Julia. And then based on that, we'll finish off and we'll go into multiple dispatch and give lots of examples of how to create types, use multiple dispatch to your advantage, and that will place you in really good stead for doing that in your projects. So that's the plan. Any questions? Cool. Oh well. Excellent. We'll reconvene on Monday. Good luck with your big homework. Thanks, Byron. What's the best way to quit this? This one? All right. See you guys.